All right, finishing up with the idea of mass arrangement. We'd like that mass to be exposed to the interior so it can exchange heat with the interior air. We'll talk a little bit more about thermal mass in the subsequent sections here. Just remember that if you cover that concrete with carpet, if you cover that stone with furniture, with cabinetry, anything like that, then you have to take away that amount of thermal mass. It's not really having the ability to exchange with the interior air. One of the points of this matrix really is to just open up all the opportunities that you have as a designer for where to put mass and what kinds of materials to use for it. You'll see on the upper right there, the Rio Grande Nature Center. We'll see that in just a second. That's by Antoine Predock. And those tubes you're seeing there are actually water, and they're lighted and heated from above. So there's a kind of nice architectural lighting effect at the same time, using it for thermal storage. All right, let's talk about types of materials. So here is a chart called diurnal heat capacity for direct mass materials. Let's break that down. Diurnal heat, that just means 24-hour or daily heat capacity. That's the kind of heat that can come into the mass and get back out in 24-hour cycle. So remember that it takes some time. The mass has as one of its characteristics that it takes time for the heat to move through it. It's got a big thermal lag. And the second part of this title is for direct mass materials. We're going to make the distinction that we made earlier. Remind you here that direct mass means mass that is in the room which is heated by the sun. It does not have to be heated directly by the sun. It does not have to have the sun shining on it, but it is in a direct gain room, or it's in some other way heated by the sun. So for instance, mass behind a trom wall, that counts. Mass in a direct gain room, that counts. Mass in a sun space, that counts. Mass that's heated by air moving from one room to the other, that mass doesn't count. That's indirect mass, right? But it has, so this is just strictly for mass, direct mass materials. Okay, so on the right you see stone, brick, rammed earth. What's the distinguishing characteristic of those materials thermally? The distinguishing characteristic is density. So in general, the more dense a building material is, the more capacity it has to store heat. So stone is more dense than brick. Stone might be 160 pounds, 170 pounds per cubic foot, depending on the type of stone. Brick might be 125 pounds per cubic foot. Rammed earth might be somewhat less, perhaps 100, right? Okay, and you'll see that reflected on the chart. So thickness in inches is across the bottom, and that diurnal heat capacity, just call that how much heat can be stored in that material on a 24-hour basis. We've got BTUs per degree Fahrenheit per square foot, right, as our units. And you can see that from 0 up to about 4 inches, almost all of those mass materials, including adobe, are pretty linear, right? So you add an inch and you get more, an equivalent amount of heat storage capacity added. Depending on the material, that curve starts to flatten out, right? With stone and concrete, it's up closer to 6 inches. With adobe, it's down more closer to 4 inches, right? And brick is kind of in between. So what does that tell us? It tells us that, number one, you can't just keep adding thickness, right? So the volume of mass for thermal storage is sort of less important than the area. And really, what we want is 4 to 6 inches of the material, which is then distributed in as much area as is required to store the amount of heat that we need to store in the building. Okay. Now, so with that in mind, we can look at sizing direct thermal mass. For direct gain rooms and sun spaces in this case, the size of the thermal storage wall is the size of the wall or the size of the glazing, right? Um, there's a little video on thermal mass that has lots of illustrations and goes through this in somewhat more detail. By the way, on the upper right, you'll see that little nature center by Antoine Predock that I was talking about in the previous slide. And you can see the tubes, those translucent plastic or fiberglass tubes of water that's being used for the thermal storage medium. They're heated by south-facing scoop skylights at the top, bringing both light and heat down into the space. And then, a supermassive building. I mean, probably there's plenty of thermal storage in this building just from the concrete and the fact that it's earth sheltered and so forth. But it adds a nice lighting effect at the same time. All right, so sizing direct thermal mass, you start with your solar savings fraction at the bottom. The solar savings fraction, what's the portion of heat I can get from the sun during my heating season? That solar savings fraction, as you might remember, comes from the solar aperture strategy. So first, we want to size the windows or the apertures to the amount of heat that we think we can get in that climate. And again, that's going to depend on size of windows, but also window technology. And, is it an R2 window, an R5 window? Is it night insulated, and so forth. So we end up with a solar savings fraction. You can also calculate that in the SWL tools, the tab for solar heating. So let's say in the example here, let's take 50%. You start with a 50% solar savings fraction at the bottom. You come up to one of the diagonal zones or lines for the kind of thermal storage that you're interested in. Let's say that we came up and to the top of the zone for 4 to 6 inch concrete. That's the top of that zone is going to be more like 6 inches. The bottom would be 4 inches. So near the top, I take my 50%. That gives me just about 3.0, right? If I hit that line and go left, 3.0 for the mass area to solar glazing area. That means I need 3 times the surface area of exposed mass in the building as I have of solar collection area. If I have 100 square feet of south-facing glass in my room, I need 300 square feet of exposed 6-inch concrete. Actually, that was 4-inch in my example, 4-inch concrete. Okay, so that's just a ratio of mass area to solar glazing area. Pretty simple. Again, watch the video and you can get a little demo of that. Check this out in the thermal mass strategy in Sun, Wind, and Light for details. Here's our Rio Grande again. In Albuquerque, Antoine Predock, really interesting architect. Check him out. Water as thermal storage and lots of concrete. Now, we said indirect is in a room that doesn't have the sun, right? So that's mass from, let's say, an air collector system or mass that is being heated by, for instance, air that we've moved from a south room over to a north room, right? It doesn't work as good. You need more of it to do the same job. You can see that the solar savings fraction on this sizing chart stops about 60%. So you're not going to use all indirect mass for 100% of your solar heating or for some high solar savings fraction. It can be a supplement, but we really advise to always use some direct mass whenever you can. Okay, it works the same way. You start with solar savings fraction, you go up, you find the kind of mass material that you're interested in. The high density materials, you need less of them. The low density materials, you need more of them. And it works just the same way. So we got mass area to solar glazing area, in this case for the indirect mass. Now, if you've got some indirect and some direct, you can use a combination as long as your total solar savings fraction adds up to what it was that was predicted in your solar apertures tool or your sun, wind, and light tools Excel file. We really do recommend using the SWL tools because it gives you a lot more control over a number of variables to end up with a net solar savings fraction. And then finally, you can use this chart again in the same strategy in sun, wind, and light called thermal storage. In this case, it's for phase change materials. Now, for phase change materials, there's a lot of stuff out there on the market. You have to go to the manufacturer. You have to look at the specific product that you're interested in. For instance, Delta Cool tiles, that gives a value on the chart here of 112. There's no line for that, but you can see the line for 100. So we've just put in some examples of the kind of BTUs per square foot of material that's exposed of that product. So Delta Cool tiles might be it's a phase change material that's built into a ceiling tile. You have a drop-in ceiling, and you can use that for thermal storage, right? So same way, start with solar savings fraction at the bottom. If you see the example of 72% solar savings fraction over on the right, come up to a material such as a bio-PCM thermat material, right? That comes in various thicknesses. If let's say you had one that gave you a performance of 200 BTUs per square foot, go over to the right, and that's about 2.5 in terms of mass area to solar glazing area. What's really cool, one of my favorite ones, let's see if this, yeah, GlassX. That GlassX window on the near the bottom, that's pretty interesting. It's a German product. It's a thick double glazed window. So you could be looking at 2 or 3 inches of space, really thick window. But in between is a phase change material. So if you put those on the south side, they'd be warming up, and the window itself is both collector and storage. Pretty cool. Downside is you don't get a view, you do get some translucency to that. So you get some daylighting, but not necessarily some view, but solar heating and storage, pretty neat. Anyway, that's the end of this little lecture about passive solar heating and passive solar systems and thermal storage. See you next time. Bye.